Thank you, Marco. Let me try to share my screen. Hopefully you can see it. Please let me know if you're on the screen.
Yep.
As Marco said, quantum machine learning is probably one of the very few areas of quantum computing where we have a realistic chance to observe some first signs of quantum advantage on the NISQ processors. Specifically, we can look at generative models. We can use parameterized quantum circuits to generate new samples from the learned probability distribution, or we can train a parameterized quantum circuit as a quantum neural network that works as a classifier. So on this page, we have a schematic representation of a binary classifier. It's very new type of research. I believe the first quantum neural network was proposed only several years ago in a paper by Fari and Nevin from Google. And the idea is that if you look at the quantum circuit, where we have a number of quantum registers and 1 qubit and 2 qubit quantum gates operating on these quantum registers, then the circuit looks very much as a network. Obviously, neural network is a little bit of a wrong term. Quantum neural network is even further from real neural network in comparison to classical neural network, but because the end result is a classifier or a generative model, we use the same terminology. So it's a little bit of an abuse of terminology, but nevertheless is more or less generally accepted now. So how it works? We start with a sample, as always in supervised machine learning case. We have a data set of samples. Each sample has a number of features or attributes, and then the sample is being processed by the network. It can be like a black box, and inside this black box we can have different models. Classically we can build a neural network, or we can build a random forest, or we can build some other types of classifiers, say support vector machine and so on. But given a sample, we process the sample through the network, and then we have an output. In the case of a quantum neural network, the sample will be processed by applying a sequence of 1 qubit and 2 qubit quantum gates. These gates can be fixed, for example, control not or control Z or swap gates, or they can be adjustable gates. For example, rotations around x-axis, y-axis, z-axis by some angle in the case of 1 qubit gates. And then finally we would have the measurement operator that would give us the answer. If we have just one measurement operator, then effectively we built a binary classifier. So the output would be either 0 or 1. We have 2 class labels. But we can have several measurement operators in the last layer of the network, and then we can have a multi-class classifier. So the question is, first, how to encode a classical data set in the quantum state, which is the input into a quantum neural network. And second question is how to train this network. So classically, neural networks are trained with, say, a backpropagation of error using a gradient descent method. Or we can use some other techniques to find an optimal configuration of network parameters. Classically, we would have network weights and biases, and we would try to find the optimal configurations of weights and biases that will give us the best possible classification results. So the question is how to do it quantumly on the quantum circuit. Before we look at the answers to these two questions, let's first recognize the fact that we are working with the NISQ quantum processors, which are relatively small. So we operate on several tens of qubits. Noisy. So our quantum gates are not perfect. It means that we should probably not have too many of quantum gates in our circuit. Otherwise, the total noise would be overwhelming. And very importantly, the connectivity is quite limited. On this page, we see a schematic representation of Rigetti's Aspen system, where qubits are essentially connected only to their nearest neighbors. And moreover, they're mainly connected in a linear kind of fashion. So most qubits are just connected to one qubit to the left and one qubit to the right. Only a handful of qubits have three connections. So they form a bridge between several islands of linear connectivity. However, even this relatively simple graph is capable of building reasonably powerful quantum tree networks, which we can see on this page. So with just 8 quantum registers and using a relatively small alphabet of quantum gates, we can build a network that resembles a tree network. So, for example, qubits Q1 and 2 are connected, and qubits 3 and 4 are connected directly, and then we would connect first 2 qubits with second 2 qubits, and so on. And then we would put as a measurement operator on the final qubit. So 2 qubit gates are here to realize the entanglement. So the qubits are correlated and information is shared. And 1 qubit gates are adjustable gates. 2 qubit gates can also be adjustable. They don't have to be fixed. But for the sake of simplicity and to make sure that the network is not too complex, we usually leave 2 qubit gates as fixed and only adjust parameters of single qubit gates. Now, let's start with the first question. How do we encode classical data into quantum state, which is the input into quantum neural network? Let's have a look at the canonical representation of a qubit state, which is a point on the Bloch sphere, which is a unit sphere. Quantumly, we can look at state of a qubit as a unit vector in the 2-dimensional complex vector space. Looking at the Bloch sphere representation of a qubit, we see that a point on the sphere can be uniquely determined by 2 variables, 2 angles, theta and phi. Theta is defined on interval 0 pi, and phi is defined on interval 0 to pi. It means that a single qubit has a possibility of encoding 2 continuous variables, which is essentially extremely powerful observation. If you would think about a classical situation, a single classical bit can encode only a single binary number, is a 0 or 1. But quantumly, a state of a qubit can encode 2 continuous variables. So enormous amount of information can be stored in a state of a qubit. After measurement, we can only extract 1 bit of information. So we can choose particular computational basis and before measurement, and then the end result would be either 0 or 1 in the chosen computational basis. But when we perform operations on a qubit, when we apply quantum logic gates to the qubit state, we operate on essentially a very complex object, a state that encodes two continuous variables. And we are using this fact to encode classical data into quantum state, into quantum registers. So let's look at our graph, which is a tree network specified on 8 quantum registers, on 8 qubits. First, we would look at a data set with some number of features, and we can encode first 8 features as rotations around x-axis applied to the corresponding quantum registers. So we would take feature number 1, we would look at the value of this feature, we would then map a value of this feature, some continuous variable, into an angle, rotation angle on interval 0 pi, and then we would apply rotation around x-axis to the first qubit. Then we do the same with the second qubit. So second feature would be encoded as a rotation angle applied to the second quantum register, and so on. In this way, we can encode first 8 features which can be continuous variables as rotations around x-axis. And then we can do the same with the second 8 features, second set of 8 features, where we would encode feature values into rotation angles around y-axis, also defined on interval 0 pi. So a relatively simple quantum neural network with just 8 quantum registers is able to support a data set or operate on a data set consisting of up to 16 continuous features, which is an enormously powerful result in its own right. So let's look at one particular example which can be implemented and realized on the proposed quantum neural network, and look at the results. The use case here is a well-known data set from UCI machine learning repository. This is Australian credit approval data set, so very relevant from a finance perspective. The data set consists of 690 samples, so reasonably large, but still relatively small, such that many classical classifiers would struggle to learn the underlying distribution. The data set has 14 features and a binary class label 01, which corresponds to credit application being either accepted or rejected. And 14 features would represent various attributes of a creditor. From a machine learning perspective, it doesn't matter what these attributes are. We just take them as inputs. The features are actually a combination of binary, integer, and continuous features, so it's a very rich data set. And we're applying our proposed encoding scheme. So first 8 features would be encoded into rotation angles around x-axis, and the last 6 features will be encoded as rotation angles around y-axis. So every single sample in the data set would be encoded as essentially a vector of rotation angles. And then the network is organized in the following way. It's a tree network, as specified before, where we choose control Z as 2 qubit gates that create entanglement. Control Z are native 2 qubit gates on Rigetti's chip. So it's a hardware-friendly implementation. And we have 1-qubit gates such as Rx and Ry, rotations around x-axis, rotations around y-axis, by adjustable angles. So here we have in total 7 fixed 2-qubit gates creating entanglement, and 15 1-qubit gates with adjustable parameters. And the task is to train this network, find such combination, such configuration of rotation angles theta that the measurement on a given sample will give us the correct answer as frequently as possible. There are several techniques how a quantum neural network can be trained. We can apply traditional gradient-based optimization, very similar in nature to what we would do with classical neural networks. Classically, we have a task of finding an optimal configuration of weights and biases. And we can, and the training process would consist in calculating the gradient and then adjusting the network weights in the direction suggested by the gradient. We would calculate first derivatives of our cost function with respect to every individual weight, and then we would apply a small update at each iteration. Would apply a small update to network weights, which is controlled by the learning rate. So that's how gradient-based optimization works classically. And the same can be done here quantumly. We can do the same with where we would apply updates to rotation angles theta. However, there are other methods which in some cases work better. Gradient-based optimization works well when we have a relatively simple cost function. Cost function which is not heavily nonlinear without too many spikes. But once the cost function becomes strongly nonlinear, gradient-based optimization may lead to finding some local minimum, and then we would be trapped in this local minimum, and we would struggle to find a global minimum of our objective function. So other methods, such as evolutionary search heuristics, particle swarm optimization, or genetic algorithm, can be used to find true global minimum, or at least getting very close to true global minimum, which may work better in some cases. And that's what we did. We applied particle swarm optimization algorithm, relatively simple evolutionary search heuristics that searches very efficiently searches the space of possible solutions. And for this particular data set, we found an optimal configuration of rotation angles. Here, we actually used a quantum simulator. So results presented on this page are results from a quantum simulator, not actual quantum hardware. So these experiments are still ahead of us. But on the quantum simulator, which is a perfect quantum computer, we can find an optimal configuration of rotation angles, adjustable angles. And then we can look at in-sample and out-of-sample results as we would do with any classical classifier. In this case, we split the whole data set, 690 samples, into training data set and test data set, equally 50-50. The model is trained on the training data set, and then we also observe performance out of sample on the testing data set. What is very interesting is that the quantum neural network has almost the same performance on the training data set and testing data set. So very little overfitting is happening, which we will talk about in a minute. why this is the case. And also comparison with classical classifiers shows that relatively simple quantum neural network, tree network that we proposed, actually delivers reasonably good results. Here we have a QNN classifier that achieves average F1 score between class 0 and class 1 of 0.85, which is in the middle of the range of F1 scores observed for optimized classical classifiers. And here we have most widely used classical classifiers. We have logistic regression, we have random forest, we have a neural network, multi-layer perceptron classifier, and we have a support vector classifier. So QNN classifier achieves results right in the middle of the range, which is a very solid result because essentially we haven't played at all with the network configuration. We proposed a tree network, and we haven't even attempted to try a different configuration of two qubit fixed gates. For example, we can add more 2-qubit gates to improve entanglement, or we can have another layer of 1-qubit gates giving us more control over rotation, so we would construct more complex quantum state on which measurement will be performed. So without essentially any optimization going into QNN, we have quite a decent result. It also means that there is a scope for improving these results. For example, quantum neural network can be constructed in many different ways, and we can have a collection of slightly different quantum neural networks with slightly different configurations of 1-qubit and 2-qubit gates. And then we would apply a traditional boosting approach where different quantum neural networks, slightly different quantum neural networks would perform classification, and then we can combine these weak classifiers into a single strong classifier with, say, majority voting approach or some other way. But what is very interesting is how QNN results compare against classical neural networks such as multi-layer perceptron. I mentioned that QNN achieves a very good result in terms of regularization, so we don't see big difference between performance on the training data set and the testing data set. So F1 score is actually the same in sample and out of sample, which implies very strong regularization, a very desirable property for neural networks. Classically, simple feed-forward neural network such as multi-layer perceptron has a parameter that controls degree of regularization, and regularization is achieved by introducing a penalty term to the cost function. Traditionally, we tend to apply L2 regularization penalty, but it can be L1 regularization penalty or some other kind of penalty added to the cost function that would force some of the network weights to become smaller, or in some cases even zero. In the case of L2 regularization, parameter alpha forces network weights to become progressively smaller. So the larger value of parameter alpha, regularization parameter, ensures that network weights becomes smaller, and it also means that network becomes more linear in a way. And degree of regularization can be estimated by calculating the so-called Lipschitz constant. Lipschitz constant is something that reflects by how much the matrix of network weights would stretch the input vector, the signal. When Lipschitz constant is very large, it means that the input can potentially be stretched a lot. So it implies a very strong nonlinearity in the network. And it is just responsible for the fact that for small values of regularization parameter alpha, we observe very different performance in sample and out of sample. So in sample, we have perfect classification, but out of sample classification is substandard. As we start increasing alpha, Lipschitz constant goes down, and performance in sample declines, but performance out of sample improves. So we introduce more and more of regularization, and overall network performance improves. At some point, we reach the best possible outcome. In this particular case, for this particular data set and particular configuration of classical neural network, multi-layer perceptron, the best result is achieved with alpha equal to 40, where performance in sample and out of sample are the same, and actually the same as quantum neural network. However, this point is unstable. Increasing alpha even slightly leads to complete collapse in the classical classifier. So the classical classifier stops learning and stops producing reasonable predictions. It is also reflected in the fact that Lipschitz constant drops several orders of magnitude with small increase in alpha. When alpha goes from 40 to 50, the network stops working, which is a very undesirable property. It also means that when we work with classical neural network, regularization is hard to achieve. It's very hard to find an optimal configuration of hyperparameters for the network, and the network may systematically underperform. But quantumly, due to the fact that a quantum neural network can be represented as a unitary operator, essentially the whole quantum circuit can be mathematically described as a single unitary operator, linear unitary operator, with Lipschitz constant being by construction equal to 1. And such a linear system, such a linear operator would always lead to very stable results and would always deliver strong regularizations. So the next step in our research would be to conduct experiments on actual quantum hardware. So that's the next step. And then over time, we would expand and build networks on larger and larger systems. And at some point, when a number of qubits increases, we would reach the point where the quantum neural network can no longer be adequately simulated by the corresponding classical system. So this is a point when we would probably see first tangible real signs of quantum advantage. But even here on this relatively small data set with a relatively small network, we already see some serious positive features achievable with quantum neural network. Potential ways in which quantum neural network would outperform classical counterparts. So I'd like to stop here